Okay, let's take a look at a couple examples dealing with free fall motion and also some of the primary concepts that we see occur throughout this type of motion. Now, with free fall motion, again, this is when an object is moving through the air solely under the influence of the force of gravity. So that means, again, no air resistance, no wind, no friction to worry about, right? It's literally just gravity acting on the object. So because of this, we get symmetry in free fall motion. So let's say we take an object and let's go ahead and I don't know, we'll draw some grass right here. Right, so there's some grass and arbitrarily some blue ball starts on the ground and it gets somehow projected straight up in the air. Right, so it goes straight up, it slows down, and then it comes right back down to the same height. Right, so we have the starting point at the bottom. So here is where it starts. Here's where it ends. And now here's what's really unique about free fall motion. If the starting point and ending point are at the same height, the speed is going to be equal and opposite, right? So if we know the velocity at the start, it will be equal and opposite to the velocity at the end. Think about this. If the only force acting on it is the force due to gravity, which means it is going to accelerate at the same rate. If we know how fast it starts, it is going to accelerate at negative 9.81 meters per second squared until it reaches what is known as the apex, right? So at the very top here, right, this is known as the apex. The apex is the max height. So at that maximum height, the velocity is 0. Now, I'm not going to call that max height an initial or a final velocity because we don't necessarily know that. If a question states, hey, when it reaches the maximum height and it refers to that max height as the final conditions, then we could call that V of F. Sometimes, if an object starts at its maximum height and then drops down, that could actually be the initial velocity. An example of that would be if you just hold like your pencil at arm's height and you drop it. There, the initial velocity would be 0 because it's starting at the apex, it's starting at the maximum height. So the symmetry that we see here then is the velocities on the way up will be equal and opposite to the velocities on the way down. So at the halfway point, right, so let's go ahead and say that we were to look at, I don't know, this point right here where there's the x. And let's say at that location, the velocity was 10 meters per second. Well, the equivalent height on the way back down, so if again we go right there, the equivalent height on the way back down, that velocity would be negative 10 meters per second because of the symmetry that we have. And really, what that acceleration shows us is that on the way up we slow down, on the way down we speed up, and it's going to occur at the exact same rate. Now let's talk about time. Right? So if we draw a different scenario here, right? So same deal, right? We'll go with a set of grass. But now we're going to break the motion down into two distinct parts. Okay, so we're going to look at on the way up. So going up will be over here. We're going to have our highest velocities at the bottom. So here we're moving our fastest. Here at the max height, our velocity is 0. Again, because we're at the apex. And at the apex, it stops moving. And think about why that is. When an object moves upward, it's going to slow down, slow down, slow down, slow down. and eventually it stops moving upward. The saying "what goes up must come down" only happens because it stops moving up. And it stops moving up, but it's not yet moving down, and then it begins to move back down. Right, so if we look at what it is moving up here, we go with a different color, it's going to take some amount of time to reach that apex, right, whatever it happens to be. On the way down, right, so now let's do this in like kind of this purple color here. Now let's say we're going from the apex, and now we start falling. Same deal. Our velocity is 0 at the top. We're moving our fastest at the bottom. And the time interval to do so is actually going to be the same. Right? So the time going up is going to match the time going down as long as the heights are the same. Right? So if our launch height goes up to the apex and then back down to where we launched it from, our time interval is the same up as it is to go back down. It's kind of it's a parabolic idea without actually drawing the parabola, right? And that's, again, some of the symmetry that we get to see in this motion. So if we come down here and quick do an example, a watermelon is shot straight up from a large slingshot at a velocity of 22.2 meters per second. What height does the watermelon reach, and how long is it in the air, assuming it lands at the same height it is launched from? So if we draw this, so we'll go ahead and sketch this one out here. So there's our grass. Watermelon is green on the outside, so we're going to be here. Now I'm going to draw this at kind of a slight angle just so we can see it go up and come back down. Just know that it is shot straight up and it's coming straight back down. So we're going to have our highest velocities. We're then going to slow down, reach our apex, and then come back down again. Right, so we're going to be something like this. Something like that. We're going to be moving upward here. I'm just going to get rid of the grass so we can make this easier to see. Right, so we're moving upward and then moving downward. Right, so going up. Here we are landing and we're going down. Right, just so we can kind of differentiate here. So things that we know right away, and we can label this. We know that the velocity at launch is 22.2 meters per second, which means when it lands, because it says we're assuming it lands at the same height, the velocity that it lands at will be negative 22.2 meters per second. Now I'm going to call this an initial, and I'm going to call this a final. We know based on symmetry at the apex, the velocity is going to be 0 meters per second at the top. So writing down our variables here, right? What height does that watermelon reach? So if we want to write this stuff down, I'm not truly going to include the VI and the VF yet, but I will include that apex one. Actually, no, I will go ahead and include all those. So if we break this down, delta Y is what we're solving for. We know the initial velocity is 22.2 meters per second. We know the velocity at the max height is 0 meters per second. We know the final velocity as it's getting back to the bottom is negative 22.2 meters per second. Because we're in free fall, G is negative 9.81 meters per second squared, and delta T is what we're solving for in the second one. So if we look at A, what height does the watermelon reach? The formula that I would advise going with would be VYF squared equals VYI squared plus 2G delta y. Reason why I'm going to choose this one is I don't know time yet. Could I find time? Sure. Do I need it? Not necessarily. In this context, because we're looking at maximum height is going to be at the apex, so our final velocity is 0, and 0 squared is just going to be 0. Our initial velocity, 22.2 meters per second squared, plus 2g delta y is what we're solving for. So if we subtract this over, right, we're actually going to end up getting a negative value. So this will work out to being negative approximately 493 meters squared per second squared after applying that squared. And that's going to equal 2 times negative 9.81 meters per second squared times delta y. Divide that 2 times negative 9.81 over, and that's going to help get rid of our negative here. So our max height that we're going to reach will be approximately 25.1 meters. That's going to be our max height that we're going to reach. Now in B, right, so if we go to B, how long is it in the air? We have a few different ways that we could go about this. What I think is going to be the easiest way would be VYF equals VYI plus G delta T. That's what I believe is going to be the most direct path. Now we have two ways that we can do this. All right, so we can look at option 1. And option 1 is going to be assuming we go to the apex. So our final velocity will again be 0. Our initial velocity is 22.2. G delta T. So we subtract over. Again, we're times delta T right there. And by doing this, we get an answer of 2.26 seconds. But the problem is that's just to get to the apex. And we want the time it is in the air. So it's total hang time. So we're going to want to double this. Right? So double that. So really, the total time that this is in the air is 4.52 seconds. That's option 1. Option 2 is we assume that the final height is the same as the initial height, which it says in the question. So that means our final velocity is negative 22.2. Our initial is 22.2. And then we're G delta T. I'm running out of room over there, right? So we know G is negative 9.81. We go ahead and work through the math on this one. And we would get negative 44.4 meters per second equals G times delta T. And in this case, we end up getting the full time of flight because we are making the assumption that the final velocity is equal and opposite to the initial velocity based on the statement that it lands at the same height that it is launched from. Both methods are equally valid. They both show the symmetry that we see within free fall motion as long as our heights match. That ends up being the kicker there. So there's your quick example to work through some of the math using the problem-solving method that has been introduced to you all. And there is just some of the concepts of free fall motion that are going to be important for your understanding of the content.